You might call this implicit differentiation part 2, or you could call implicit differentiation related rates lead up. In other words, implicit differentiation gets you to being able to use related rates. It looks like a pretty short list, and it is, and it's pretty simple too, really. If you got everything up to this point, this won't be too hard. You might find it interesting though. Variables. Some of them are related, just like some people are related. That's about as far as we're going to go with that though. So here's an example. Y equals 2x. The x and the y's are related. The y values are double the x values. Real simple. We can take the derivative of that using our related rates. Remember, quite often with related rates, we're talking about something changing over time. So keep that in mind. A lot of the times when you're doing implicit differentiation, it might be with respect to time. So expect that, but be careful. It could be other things too. For example, price can change depending on what the demand is, or vice versa. So we've got an example for us to play with. We've got a relationship here, an explicit one to be exact. Y equals x squared plus 3. That looks pretty simple, but for the fact that we're going to be differentiating with respect to time. We've got a rate that involves time. And what we want is, we want to find out what's dy dt. How is y changing when the x value is 1 and the x value is changing at a rate of 2 per second or 2 per minute or 2 per hour or whatever it is. We're going to use a chain rule. That shouldn't be any surprise. Chain rule with implicit differentiation. So here's the original equation. We'll differentiate that. So we split it up into individual terms. Take the derivative of y, the derivative of x squared, the derivative of 3, and all of those will be with respect to time, not x. So what do we get? Applying the chain rule, we've got dy dt. Remember, that was just a y. And what we had is just 2x, or x squared rather. It gives us dx dt. If we want to look back here, here's our original one, y equals x squared plus 3. Remember, we're differentiating with respect to time, however. So the y, oops, how did that happen? The y we're going to differentiate with respect to time, so that's dy dt. This one, you get the 2x, but you're differentiating the x, remember chain rule, so you'll have it at dx dt at the end, and this gives us 0, so we don't have to worry about that part. So that's what we get applying the chain rule. And here are our initial conditions. When x equals 1, whatever x represents, and when x is changing over time at the rate of 2 per whatever the unit of time is, just put those numbers in, put the x value in, put the dx dt value in, and bingo, out pops dy dt. That's how fast y is changing. This is the rate you were looking for. So let's solve some related rate problems. Here's an example. You drop a stone into some water and you get ripples. You've seen that. You get concentric circles just like in the picture. And the radius of the outer ripple, that's the part out around the edge, is increasing at the constant rate of 1 foot per second. So every second, the current ripple is moving 1 foot. When it gets out to 4 feet, what's the rate of the total area? Oh, that's interesting. Where'd the area come from? Well, we know these are concentric circles, and we know that the area of a circle is related to the radius by A equals pi r squared. That's familiar. To solve that, you're going to use the fact that the rate of change of the radius is constant at 1 foot per second. That was given. So dr dt, this right here, the radius is changing at 1 foot per second. This is just another way of writing. The radius is changing at the rate of 1 foot per second. So that's one of those things you want to write down as a given, only in symbolic terms. There's your equation. We've got two variables. We've got the area, it's changing, the area inside the ripple, and the radius of the ripple is changing. So we're going to take the derivative of that, and you might write these down as what you're working with. There's the equation you're working with. This is what you're told is how fast the ripple is moving, the edge of the ripple, and you're interested in particular when the radius gets out to 4 feet. And what you want to find, so it's nice to have everything in one box. That way you don't have to go back to the paragraph, read through it several times, and that can be really annoying. So here's the equation, the basic equation. You can find that sometimes in the backs of books, or if you're desperate, hey, you can always Google it and find out what the relationship is between the area and the radius. Here are things you're given, and you're looking for how the area is changing per second, per minute, whatever it is. So we start with the original equation. We're going to differentiate with respect to t, because we're talking about things changing over time. Apply the chain rule. dA dt, that's the area changing over time. 2 pi r squared. Remember, the 2 is a constant, and the pi is a constant too. The Greek letter pi looks a little bit like a variable, but remember, it's a constant for circles. So when you bring this 2 out front, you also bring the pi out front. So just work with the r squared. You get the r, there's the 2 from the exponent. And because you're doing it with respect to time, you don't have dr, you have dr dt, and there's your dr dt. And there's your differentiated function equation. Now you can take a look at some of the numbers that you're getting. You can take a look at what's happening when the radius of the ripple is 1 foot, when it's 2 feet, when it's 3 feet, when it's 4 feet. What's the area? Well, as it's at 1 foot, when it's at 1 foot, the area itself is increasing at 2 pi, or about 6.28 square feet per second. At the radius being 2 feet, the area is changing at 4 pi, or about, what is that, 12 and a half square feet per second, and so on. These are some guidelines you can use. If you do several of these questions, maybe 5 or 6, you ought to get pretty comfortable with it. One note, remember, you're going to use the chain rule, and you're going to quite often use implicit differentiation. Keep those main things in mind. Now, there's some other things we use. It isn't always the area of a circle, of course. There are lots of other possibilities. Another one you might see quite often is the volume of a sphere of radius r. One example that I know you are likely to see is maybe a balloon, for example, being blown up. And you know how fast the air is going into the balloon, and the faster the air goes into the balloon, the more the volume is, and of course the radius is going to get bigger. As you blow into a balloon, it gets bigger. Here are some formulas you might run into and some related expressions. Notice miles per hour, cubic feet per minute. Take a note on this one in particular. It says dt. That means you have to be careful. Is it per minute, per second, per hour, per year? What is the change in time units? Also, what do you have on the top? In this case, it's volume. Volume is a certain distance cubed, so it might be cubic feet, cubic yards, cubic meters. Keep that in mind too. That makes it easier when you get to the end of the problem that you have the proper units. This is a population example right here, and you'd have so many bacteria per hour. X would be the number of bacteria in the population after a certain amount of time. In this case, notice up here we have minutes, down here we have hours. Watch out. Don't just put something in that you've been using for a while. Maybe you'll get in the habit of putting minutes in all the time or seconds. Be careful. Revenue, that's a good one, per month. It could be per day or it could be per year. Watch out what you're doing. Be careful. Profit, so many dollars per day. Also notice that this is a negative $2,500 per day. That means the profit is dropping quite a bit every day. So whatever is happening, you better check that out as a business owner. So here we have another example. We're producing some kind of a product, and we're creating 200 of them per unit, 200 units of them per week. So maybe 200 TVs or pens, whatever. Just make up something of your own. It's best, I think, to make these things feel a little bit personal. Make up some kind of a business that you're using. So we're talking about 200 of those things every week. So there's your time unit. The demand function, remember that always has P and X in it. P is the price for each item. X is how many items. That'd be how many you could sell or how many you're producing, whatever the situation is. You want the rate of change of the revenue. And notice it's in dollars. Don't get to the end of a problem. Work some fantastic magic on it and put in dollars, and maybe it should have been euros or pesos or marks or something else. So be mindful of what you're doing. It says Find the rate of change when the weekly production is 2,000 units. So you want dx dt when x equals 2,000. Now, excuse me, dr dt, because we're talking about revenue. The big question is, and maybe this is what your boss asked you, is the rate of change of revenue greater than 20,000 per week? Let's find out. Now, you already know that your production is going up 200 units per week. These are the units. T is going to be in weeks. So dx dt is one of those things you're going to write in a box somewhere, because when you do your differentiation, all that work, dx dt is going to be in there somewhere, and you're going to need to replace it by a 200 to get your particular result. So here you got the given rate is dx dt is 200. You want to find dr dt, remember, change of rate of revenue when the x is 2,000. Don't get these two mixed up. Remember, this is how the item is changing, the demand is changing, 200 more units every week. And this means we're selling 2,000 of them. These are different things. They're related, but they're not the same thing. This refers to dx dt, and this is x. So first of all, you can't go anywhere unless you have some kind of an equation that relates the revenue and the number of units. How do R and X relate to each other? There you go. This is one of those things you ought to have in your head and not have to go to some kind of table somewhere to find out. Revenue equals number of items times the cost of each of those items. If you were stuck on a desert island and you wanted to remember what that was, just give yourself an example. How much money would be coming in, that's revenue, if you sold 17 items for $100 a piece? And that'll give you X times P. And you'll be in business. So here's the X. We already got the P part earlier. So this is the revenue part. In yellow, I'll put your revenue equation. R equals the 100x minus 0.001 x squared. There's your revenue equation. You're going to write that original equation down. You're going to differentiate it with respect to time. Remember, time is going by. How are things changing? How is the revenue changing? That's going to be this one. And this has to do with the demand. You're going to differentiate that with respect to time. Applying the chain rule. There's the derivative of R with respect to time. And on the right-hand side, you'll end up with 100 dx dt and minus 0.002x dx dt. It's already factored out. Put those numbers in. We said dx dt was given to us. It's increasing at 200 per week. And we're selling 2,000 of those each week. Just put the numbers in. The revenue is $19,200 per week. Remember, dollars and week. Very important. But the question was, how does that compare with 20,000? Well, it's not greater than 20,000 per week. That's your answer. Remember, you're answering a question. When you get to the end, you have to be answering the question, not just throwing the 19,200 per week as your answer. That's not the answer to what was asked. So be careful, okay? So there's a start with related rates. You're going to have some good practice from the exercises in the book. If you have any question on any of them, send me a picture or type out what the question is. Show me what you did, and I'll try to get you on track. Okay? Keep smiling, and we'll see you later. Bye-bye.